Hi, everyone. Thank you for having me here at the workshop. And my name is Ramin Hasani. And today I'm going to talk about a new technology that we have been developing for better designing a neural network architecture. So my talk is about liquid neural networks for autonomous driving. So let me get started by showing you a dashboard of a typical dashboard that we usually have for end-to-end learning of tasks in autonomous driving, for example, lane keeping, where we have, like, let's say, like you have visual input, and then this visual input goes into a group of convolutional layers followed by a fully connected layer. And then let's say in this task, we want to do lane keeping and we're taking control of the steering of the car. And what you see here, the fully connected layers activations are visualized here. And then we have like the map that the car is actually autonomously driving on. And on the bottom left, what you see is the attention map of the convolutions, or basically where the network attend to when a driving decision is being made, okay, while the driving is happening. And one thing that we can see like very immediately is that like the representation that has been learned throughout this fully connected network is that like the network as a whole focuses on the sides of the road in order to perform or take a driving decision, okay? And this is kind of not optimal, so we want to improve that, because if you think about it, like when you want to perform lane keeping, you want to focus on the road's horizon, instead of just focusing on the outside world and learning to do that. On the other hand, what we see here is that the extensiveness of the neural network makes it less interpretable. So I cannot say for sure what each element of my system is actually doing. So there are questions about interpretability. There's also another issue that I would like to highlight here. Imagine if I just add a little bit of noise on top of the input images. What we see is that the attention of the network, although the network is being able to drive based on its, like the data that it has seen, and we see that the attention map of the network is scattered, okay? And it's actually highly sensitive to this type of perturbations. Okay, so robustness of these networks are also under question. So with this motivation, I want to tell you that I want to motivate like what kind of properties we want to look into these type of networks. For example, what we want to improve the representation learning in order to bring the attention of the network naturally onto things that are more causal. We want to improve the robustness and flexibility of the models when they're taking decisions so that they don't get fooled by adversarials or perturbation from the environment. And at the same time, what we want to improve the interpretability of this model. Our approach to doing so is basically looking into a class of neural networks called continuous depth models. Okay, so let me tell you about what is a continuous time or a continuous depth model. Imagine if a neural network F parameterizes not the state of the hidden state, but the derivatives of the hidden state. So neural network F with n number of layers, with K and choice of activation function. It has dependency. It receives inputs from the hidden state. Basically, it might have recurrent connections. It receives inputs I, and it's parameterized by theta. And it's actually give rise, like it's the right-hand side of a differential equation of this sort that actually can create a dynamical system out of a neural network. So this representation was shown to be extremely, it gave rise to a new category of neural networks. It's called continuous depth models. Imagine when you have a residual network. In a residual network with 6 layers, what you have at each layer, you perform one point computation. So thinking about the computation graph and each of these nodes here, we have a computation point basically. So at each layer, you perform one computation through the depths while you go through the depths of the network. But with this parameterization of the network, in ODE-based parameterization, we see that the space, the depth space of your neural networks becomes continuous. And this evaluation, if you have a differential equation of this sort, and this differential equation, you realize it with ODE solvers, then what you can do, you can perform computation at arbitrary time. So the depths of your network is not anymore defined by the layer by layer stacking of your neural network, but it is continuously defined. And this kind of representation is actually having a lot of is enabling a lot of interesting behavior that can be useful for our purpose. So for example, we know from the standard recurrent neural networks, they have a function f that for computing the next step, it's a discretized kind of equation that performs a computation. And neural ODE, or this continuous time representation, would parameterize the ODE itself. And there is also this another more stable representation of these neural networks, which have this, like a damping factor tau that brings the neural network dynamics into stability. So just to show you the impact of this thing, if you have a normal LSTM or any type of recurrent neural network and you want to fit it to a spiral that is irregularly sampled, we see that the kind of extrapolation of this network is not as smooth as a continuous time neural network. We see that extrapolation and interpolation of a network, when the samples are not arriving at an equidistant time, these networks can actually bring significant advantages. Okay. So how do we implement these type of systems? Let's say we want to implement a forward pass of a neural network of this sort. What we do, we use numerical ODE solvers. So by numerical ODE solvers, we can actually roll out the kind of this differential equation by its differences, and then we can compute the next time step by basically just this unrolling of this differentiation. And then this becomes our forward pass for computation. And now, depending on how we are unrolling this system, the forward pass of our system is going to be different, right? So you can have different, this is now an explicit Euler decomposition, but we can do with more complex settings. So anytime you have, at this time you want to perform a computation, you do a call to an ODE solver, and the ODE solver can actually compute your next step by its realized decomposition of the decomposition of the actual differential equation. How do you train these networks or backward pass? There is a method called adjoint sensitivity method that basically given a loss function and basically an end state that you want to compute your trajectory, and also like a neural network that is a neural ODE that is given by this type of dynamics. You can have a call to an ODE solver to compute from this point in time. This x-axis here is time, and you can compute the trajectory of your system, this system, forward, and you can compute a loss. And then the adjoint sensitivity method adds an auxiliary differential equation, basically that has like the adjoint state, like we have like an additional state for the network optimization that is like derivative of the loss in respect to the parameters of the system. And then what you can do, you can write that as a dynamical system again, and based on that dynamics, a backward propagation of the dynamics of our system basically can compute the gradient of loss in respect to the parameters and the state of the system. So with adjoint method, you can perform computation one step at a time computations to obtain the gradients of the loss to perform parameter updates of your network. The adjoint method is a one step at a time kind of optimization. It doesn't back propagate through the entire sequence that you had during the forward pass. That's why its memory complexity is really low compared to the other methods. There are also other methods like back propagation through time that is general for RNNs. Let's say, how would you do that with back propagation through time? We perform one forward pass, and then whatever was your ODE solver, here again, we are showing a decomposition of an Euler, explicit Euler numerical solver, and we can compute the gradients of the loss And using the chain rule, you can find out the gradients of the loss in respect to your parameters and obtain your parameters. So that's how we train this type of networks. Now, if you train it with backpropagation through time, you're actually propagating through the entire sequence. So basically your memory complexity of your computation path is going to be much larger, but the accuracy of the backpropagation is much higher compared to the adjoint sensitivity method. Now, this type of network, so I told you about these neural ODEs, they can be applied and they have been tried in different scenarios and real life applications, such as lane keeping application, autonomous racing, learning physical dynamics, and surgery, and safe autonomy, and goal understanding. But what we saw so far is that with this representation that we're showing on top, we cannot even beat an LSTM network. Okay, so we cannot really gain better performance than an LSTM network. So there's no need actually to use this type of system. So what kind of property, like these networks that are so amazing in theory, how can we bring them in practice, and how can we make like a nice network out of these things? Okay, with this motivation, we performed a modification with our colleagues, and we call it liquid time constant networks. So how does it look like? So the differential equation that I showed you before was parameterized directly by a neural network F, but now I'm saying that each node of that neural network, like X is the hidden state of a neural network, is defined by this linear dynamical system and receives an additive synaptic input, this S, and the S or synapses of your system are parameterized by a neural network. Basically, we bring the complexity or the nonlinearity of a neural network from nodes to edges. So just to have an understanding of where this is coming from. And with this modification, if I just replace S inside this ODE representation, I end up having a more complex representation, but still, it's actually a very nicely behaving dynamical system. If you look at this equation, we see that there is a neural network F that both represent the state of the neural network, and at the same time, the time constant of the dynamics. So this element here is 1/, time constant of the entire system. And based on the inputs that come to the system, the inputs to the system, to the neural network, the time constant of the overall hidden state dynamics of the hidden states is changing. Therefore, the behavior of the dynamical system changes. So that's why we call them liquid time constants. So the time constant of a differential equation is defines the characteristics of that represent a dynamical system. So if you change that, then you expect to have a different dynamical system. So at any given point in time, this system is basically evolving, okay, even after training. Now, to show you like just schematically, how does it look like compared to the traditional neural network architecture with their possible connections. Imagine I have two neurons. These two neurons, each of them, they have an activation function sigma, and they can communicate with each other one way or another possible connections that they can have with a weight parameterization. And this system can also receive an input, external input, and it's parameterized by B, and it might be a recurrent connection, so it might have also a recurrent connection like that. Now, with a liquid neural network, what we have, instead of the nodes being activation functions, the nodes of the system are actually differential equations. The connections of the system gets the nonlinearity, and this nonlinearity identifies how the correlation or how the interaction between these two systems is being identified. And that's how the representation is looking like. Now, let me show you by what it means to have a liquid time constant in the in our field of autonomous driving. So imagine there's a network that is trained on basically driving into this kind of environment. It's just a lane keeping task again. Now, a standard neural network doesn't have, like, it selects a time constant for its activity, and that time constant is actually preserved. And then on the x-axis here, what I'm showing is basically the steering angle. The color is also representative of the output of the system, which is again steering angle. Now, if you look at the liquid network, we see that the time constant, or how fast this dynamical system is behaving in different driving scenarios, it's changing, and it adds more degrees of interpretation and expressivity to our system. So let's say, for example, when we are taking a left decision making, the time constant is higher, and when we are kind of having a straight line forward, the time constant is around here. And again, when we are turning to the left, we see that the kind of time constant of the system, which is on the x-axis, again increases. So that means another degree of understanding this system in action, and we see the liquidity or the change of the time constant of the system. Now, these systems have properties, so we really started characterizing this system. So in terms of they have a state, I mean, I showed you a complex differential equation. So this complex differential equation should be stable enough to be able to work with. So it has a time constant, and the time constant element has to be bounded, so that we found bounds over its time constant. So it doesn't go to infinity and it doesn't explode, right? So the time constant of the system is basically ensures the stability of the system if it's bounded. And also the state of the system is also bounded, because the differential equation is of the what we call a bilinear approximation of a linear system. And these type of systems are proven to have bounds if you specifically ensure some of the properties of this network. Now, we also showed that this representation of ODE is a universal approximator. So basically, you can use it in theory for any type of sequential or non-sequential data processing tasks. We also looked much more deeper into expressivity of these networks. For example, for neural networks, for understanding how expressive is a deep neural network, there's a method called trajectory lengths. Suppose we have a neural network that has fully connected layers with ReLU activation functions, and the weights are initialized by this normal distribution. It has n layers and k with k. If I input a circular trajectory inside this neural network, at each transformation, at the output of each of these layers, we would get a deformation of this circular trajectory. Okay, and it was shown in a very theoretically rich paper that the complexity, the projection of the complexity of the hidden state into a 2D space increases exponentially as you're making the neural network deeper and deeper. And this can be measured by the arc length quantity. So how do you compute that? You basically take the infinitesimals on this trajectory, and then you compute the lengths of this deformation. And you can actually find lower bounds and even upper bounds for their complexity. And this complexity shows that if I give you this number of layers of neural network, your network is this much expressive in terms of trajectory lengths. Okay, so now that we have this nice, rich expressivity analysis framework, we applied this theoretical analysis on a wide range of continuous time neural networks, LTCs or liquid networks, and CTRNNs, continuous time neural networks, and neural ODEs in their plane representation. We see that basically the trajectory lengths of a transformation of a circular trajectory is larger in the simple scenarios. And then when you actually change the dynamic of the system, we see that the complexities that are generated out of this system is much higher than the other methods. So in terms of trajectory lengths, these systems, given the same amount of parameters, must be more expressive than the other neural networks. We tested it empirically against using different ODE solvers, the yellow line here always shows the trajectory lengths or the expressivity of LTC networks compared to the other models. When you increase the size of a network, when you increase the variance of the initialization of parameters of a network, or when you increase the number of layers of a neural network. We even showed this, like really mathematically found the lower bound for the expressivity of this measure, which I'm not going to go through that thing, but it's still like finding that theoretically this representation must give a better expressivity given the same amount of capacity for these networks. Now that we have like this network, now let's now go back and now compare it to those RNNs or other neural networks that are out there in a series of experiments that are possible. Let's start simple by learning physical dynamics. We see that now that we have this type of neural network, they can actually beat other types of neural networks in physics dynamic simulations. If we go to real world data sets a little bit larger than the previous one, they can also achieve a better accuracy in predicting human behavior in irregularly sampled data. We saw that in many real world data sets, they could actually give rise to a better kind of results compared to the others. We saw that if you put them in reinforcement learning environments and you sparsifying these networks, which we call ordinary neural circuits in the sparsifying neural networks, so you can also get like in simpler tasks with 77 sparsity networks, 6 nodes, you can actually beat a larger LSTM or a larger RNN network. You can perform parallel parking with this 6 node network, basically, and like from state information. And we thought about, all right, so now it's time to scale it up to doing some tasks in autonomous driving, you know, so we go from those sequential tasks to a harder task, right? So as I showed you before, like the pipeline, usually the simplest pipeline for doing an end-to-end task learning would be like a pipeline of convolutional layers followed by fully connected layers that range between 5 million parameters to 1 billion parameters, depending on what kind of task you're performing. So what we try to do, we try to benchmark against all these networks that are out there by replacing this part of the network that is parameter extensive with LTC-based networks, with LSTM-based networks, and ODE-based networks, okay, in general. This gave rise to 4 different variants that fundamentally we want to compare them against each other. That is the LTC-based network, we call them neural circuit policies. They have a 4-layer architecture. They're extremely sparse. And these are all explained in our Nature Machine Intelligence paper, where we actually showed that these systems can be super small compared to their counterparts. We have a fully convolutional, small convolutional layer because our task is just the lane keeping task, because our goal here to set a standard, where do we stand in terms of kind of expressivity, as I said, which is a measure of representation learning, and robustness and interpretability of these systems. And now comparing them also with networks that we replace their control part or the fully connected layers of the convolutional layers with these other networks. We see that in terms of parameters of RNNs, you can actually have 253 synapses and 19 neurons in the RNN compartment that performs the learning task, the lane keeping task very well. So now remember what I showed you before, the fully connected network over here with extensive amount of parameters to perform this with this type of kind of attention map without any regularization, just using these 19 neurons. We see that the lane keeping task or this task under test is performed like much better in terms of like causality. So let's go forward and see how the focus of this network, basically what we are computing as an attention map here, we are not computing the attention map of this network. we are computing the attention map of the convolutional network. That means during training, the kind of inductive bias that this network puts on the weight learning of the same convolutional layers as before is actually makes the network to focus on the Rhodes horizon. So if we add a little bit of noise, what would happen? Because now there wasn't noise. Here we see that definitely the attention map is a little bit scattered, but still it's much better than what it was before for the convolutions. So this attention is actually something that came out of this architecture without putting any prior or any regularization element. In terms of robustness to noise, if you increase the amount of input noise, here on the x-axis, we are increasing the noise. The y-axis, we count the number of active testing crashes that you want to get out of the training. You see that number of interventions that are required. We see that these networks are much more resilient than the counterparts that I just said before. And then looking at the attention map of not only CNNs that they look outside, people say, all right, so what about the other ODE-RNN? How does their attention map look like? So it's pretty scattered, as we see, like for CT-RNNs, it's pretty scattered. For LSTMs, we see that the attention on lighting condition is pretty much, so LSTMs are very sensitive to lighting conditions in these kind of scenarios, while the NCPs or the solution that we are providing here is actually focusing properly on the Rhodes horizon. Now, why is that the case? In the next study, what we try to do, we try to understand why there is this causal inductive bias happens in this system. So we try to look around and see work from causal inference, how the causal inference framework actually maps, how can we actually theoretically again and fundamentally show that these systems are causal, because we saw that in practice without any regularization. So probably this is one of the features of the network. We saw that there is this dynamic causal modeling framework that actually has the very similar property of this interaction of the nodes of a system being parameterized by a parameter. But if we look at the liquid time cluster, it's like kind of a nonlinear version of that. And in a recent under review paper, we showed that liquid neural network-based networks or neural circuit policies are actually dynamical causal models. And then we showed that, and we showed it in a variety of drone navigation tasks in 3D. Imagine, for example, here, this is an image that is a drone sees. And again, we see that, again, without a prior, if we look into the attention mechanism of different neural networks, see that the NCPs are the only one that actually from visual data learns where to look at, which is this red cube over there in the environment. So the attention of the network was actually, this is the attention of the network for different time instances, and the navigation in 3D happens. Like the objective was to learn how to go, it's an imitation learning scenario where in AirSim that you want to actually navigate towards a target, and you want to teach that to a drone just from visual data. When we do that, you see that this is actually the type of attentions that you get. Like now in action, what we see is that the drone that is navigating into this forest, as soon as a target actually gets appeared, the entire attention map of the network goes to that system. And we have 24 neurons that actually are performing this with a very small convolutional layers with 70K parameters, not in the range of millions. Again, in other more challenging environment, we also observe that the attention maps are not, basically that's like kind of confirming our experimental setting. We even extended it to leader following tasks, where we showed that now the view that we are seeing right now is from a follower drone that follows a leader drone, and the leader drone is moving towards that object, and the follower drone is basically what we are seeing. And then we looked into the attention map in this task. We see that even in this task of following, the network actually learn to attend to the right object, to the leader, right? So, and that's another testimony for why these networks are good. So we tested them in closed form and compared them, their closed form performance in this navigation task. And we see that the completion rate of these tasks is significantly higher. Like there is, for example, a task called hiking that has a long time horizon. And this task was not being able to achieve by any of these systems properly. We see that, I mean, 30% of the times that this system that is 100% trained offline, there is no online interactions, they actually performed pretty well compared to the other models in different lighting conditions like heavy rain and fog and occlusion, for example. And yeah, so I'm at the end of my talk, so I'm going to tell you two main limitations of this network, which is very important these days. So you have to, so if you think about it, like these systems are a complex ODE. And now a complex ODE is actually dependent on how complex is their ODE solver. So this might actually lead, although the size of the networks are small, but the complexity of the ODE solvers can be really hard. So basically the training and testing time might be larger. So there are solutions for that. You can use a stable fixed step solver. So if you use a fixed step solver and not a complex solver, you can actually gain a good level of performance. You can use hyper solvers. There's like a recent work, like there's a line of work on these continuous time neural networks that is out there. And I really encourage everybody to, from the autonomous driving community, to look into, because it's really exploiting the capabilities of dynamical systems in neural network design. That's I think it's a beautiful opportunity that is provided. And also you can use closed form variants. So we have another work that is on closed form variants of the same kind of dynamical system that is like around 1,000 times faster in inference and training. So you can also look into that. And another problem that we have, these ODE-based systems are, they're networks that might express vanishing and exploding gradient problems, okay? Basically, they would face difficulties in learning long-term sequences. So the longer the sequence gets, the less useful these things. And by long, I mean very long sequences, you know, like in terms of 40,000 steps and stuff, like 40K steps up. And then there is a solution. You can use mixed memory wrappers, like you can put this ODE inside a wrapper, a gating wrapper. And that's also another work that we have under review that hopefully solves this limitation of this problem. So in summary, what I wanted to bring your attention to is basically the capability of acquiring knowledge by a flexible model, a model that is liquid. And now you can use it for inference. Model-free examples I showed, you can perform very good temporal credit assignment and also understanding the structural properties of your environment. They can be used for generative models in principle, and they can be used for word modeling, like modeling the word and then using them for this type of behavior. And I can tell you that there are certain, these are kind of mathematically proved properties of these systems that I would suggest to look into. So, and with that, I would like to thank you for your attention. And here is a group of people that we're working hard on this topic. And I put the address of our technologies all open source, so you can actually access any of our technologies through this GitHub repos. And feel free to contact me if you have any questions and you want to get hands-on with our technology.
Thanks, Ramin, for a great presentation. I mean, it's really wonderful. I have been actually looking into NeurOD in the last half a year. I mean, last year I remember in a NeuroNIPS workshop, there's a great NeurOD tutorial, I think.
Right.
Yeah, so I guess it's really getting popular nowadays for this type of new technology. And I agree with you that the autonomous driving community should, I mean, always look into new technology out there in the machine learning or in other domains, not just stick with what the vision model we have right now. because that probably not will enable like a next step or like big breakthrough of the entire research. So I agree with you on that. But yeah, so through your talk, I already have kind of listed a quite long list of questions. But I guess because of the time, I probably just only ask one or two. Or if there's question from audience, you can also ask since Ramin is here. So the first question I have is regarding the model you provide, the liquid model, especially you talk about I guess two main things. One is the attention you learn through different tasks, and also you are replacing the standard multi-layer perceptron. For example, in the autonomous driving, the end-to-end pipeline you're doing, you replace the last few layers, the multi-layer perceptron or the dense layer, with the liquid network you are using, you are proposing. So that's kind of similar to the transformer. Like people are also excited right now in the machine learning community, right? So because transformer, you can use it to replace multi-layer perception, and also you can learn better attention. So how is that connected to your liquid network? For example, how can we combine them? Because right now, I guess people believe the transformer really learn the strongest attention models so far. So is that even better than your liquid neural network, or is there certain advantage of your liquid neural network in terms of attention, or is there a way to combine them, something like that?
Excellent question. So attention-based networks and transformers are forward attentions, right? So you perform a forward propagation, and then you perform the credit assignment by the transformer operator or by the attention operator, right? So in any of those tasks, the attention mechanism is actually distilling this knowledge from the environment, and that's the kind of tool to forward attention, basically what I would call. But what the liquid networks are actually imposing is, after you train a network, what kind of prior you put on it, what kind of inductive bias you put on your network. So basically, the network's attention is kind of a backward process of what I was showing you in terms of like those attention blocks. We use an algorithm called visual backprop. Okay, so visual backprop just computes a saliency maps, right? So it just shows that if you have a convolution, if you have a perception module, and this perception module is followed by fully connected layers, and you do backpropagation, the implication of fully connected networks on the learning capability of convolutional network or the perception module is something. If you have a liquid neural network or a continuous time neural network or a recurrent neural network, the implication of the weights or the type of weights that are learned from the convolutional network is going to be different. So it's kind of an, you see, like there is kind of a bit, but I can tell you that the liquid networks can be also stacked after a transformer. Transformer can extract features, and a liquid network can be used for the temporal kind of credit assignment problem, right? So they can be used with other perception modules, like if transformers are used for that purpose.
I see. So basically you're saying, okay, if we want to stack them, we can do it. For example, one layer.
Absolutely.
Okay, got it. But I guess one other question I just come up. Yeah, so when you have the transformer, yeah, never mind. I kind of just forget. But when you were just saying something, I just come up with another follow-up, but I just kind of forget right now. So maybe come to another question, which is also a main topic you are talking through a talk, which is the interoperability of your liquid neural network, right? So also you mentioned that you are able to achieve very good performance with a very small amount of neurons, right? Very small network, much smaller than what we had in transformer or in just standard multi-layer perception. So in that sense, it seems to be more possible to get a better understanding of what each neuron is doing, right? For example, if you have tens of thousands of neurons, it's really hard to know what's happening right now, because probably that's one function is being responsible by, let's say, thousands of neurons. So they're doing some combination of functionality. But here, if we only have a couple of neurons, let's say just 6 neurons, is it easier to identify, okay, this neuron is for this task, this neuron is for the other thing? Because I didn't really see that kind of experiment in your in your slides. But is that something you think of before you tried it?
That's an excellent point. Yes, that's part of the Nature Machine Intelligence paper that we have on neural circuit policy, where we actually look now, we have 19 neurons. So, I mean, you can just do a simple correlation analysis that what is the function of each node now? And you can actually do that. You know, you can really find out that there are specific neuron that if you ablate this neuron, then the function of left turning or any function in that lane keeping task is getting affected. So that's actually another nice thing about the networks. As I said, our goal was to improve interpretability. Now, through the size of reduction of the size of the network, you can just use any type of visualization or correlation analysis to actually get a really good interpretation of what each node of your system is actually doing.